My name is Ari Vanderhoeven. I'm a senior program manager on the kernel team at Microsoft, and I'm here with Lena Puthiyedath, a senior architect at Intel. And we're going to talk to you today about something completely different, because we're not talking about Azure, we're not talking about cloud computing. What we're talking about are very large systems running hundreds of processors and announcing support, as was announced this morning, for more than 64 logical processors in Windows. And this is for Server 2008 R2, but the underlying changes to the kernel also reverberate throughout the system, including Win7 client. So everything here can apply to client as well. Those are all SKU decisions. And of course, today we'll be focused mostly on server. I'm going to start with some terminology as we get going, because you can kind of get lost throughout the talk if we don't start there. We're announcing, as was announced today, up to 256 logical processor support in Windows Server 2008 R2. Windows Server 2008 R2 is supposed to be a minor release. Being on the kernel team and working on this for a couple of years, I would say that for us at the foundation of the server, this is the biggest release we've had since Windows 2000. So I don't really buy this R2 stuff. We are evolving, and we're evolving quickly, and partly because of the market and the hardware evolution, which we'll look at later, and certainly some of the motivations coming from Intel. We're also talking about application guidelines. My guess is not a lot of you write applications for these large systems. Today's focus are basically your big line of business applications, but we'll go into some kind of high-level detail there. We'll also talk a lot about NUMA today, because hand in hand with this hardware evolution and these large systems, everything is becoming a NUMA system where you have to start worrying about what's close and what's far as memory, CPUs, I/O, etc. We'll look at some system tools. We'll also have a fun look at a system running Task Manager with 128 processors. And then we'll look at the Intel Enterprise Roadmap and how that really syncs with what we're doing at Microsoft. Finally, we'll look at the future. And this is where we start to look at what we're doing here in the kernel team and how that fits in with some of the other initiatives, such as the Parallel Computing Initiative, concurrency runtime, etc. So we're seeing a big evolution in server. And as Moore's Law keeps trugging along, we realize that a CPU can't just keep getting hotter and bigger. As these things get bigger, they start to leak. We start looking at now 4-core, 8-core, 16-core systems. And as we look at the evolution of the hardware platform, we're beginning to realize that there are some systems not too far out on the roadmap that are going to be able to compete with today's big iron systems, only they'll be commodity-type systems, often running x64 processors. What that means is in a few years, you'll see systems that cost hundreds of thousands of dollars or millions of dollars today will cost a fraction of that, and they'll have similar performance and hopefully reliability numbers. So it's a real ground shift that's taking place in the server industry, and it'll be really interesting to see how things work out. This is also a space that isn't dominated by Windows. We're great on the low end. On the high end, if you look at the market numbers, you look at what Gartner puts out, it's half the market, and we're just not there. So we're very motivated to make this work, and we're betting big. And you've seen today how you've seen this week how we're betting big in other areas, such as Azure and virtualization and scaling out. But we're also making very foundational changes in scale up, and the immediate reason is this big opportunity in server for us. We'll quickly go through some terminology. If I say processor, package, or socket, I'm talking about that physical processor, what you basically see. It looks like a single chip on the system. Inside that, as you know, most sockets are multi-core, so you'll have multiple cores inside a socket. And then you get down to really what we're talking about when we say support for 256 logical processors. is a logical processor or hardware thread. And that's important because that's what applications or their operating system views. Hand in hand with that, we're talking about non-uniform memory architecture. And if I say NUMA node, I'm talking about a group of logical processors cached in memory. They're in proximity to each other, and they're exposed via via firmware to the operating system and applications. They may or may not include devices as well. We'll be talking about the term group, which is a concept of up to 64 processors, and it's really the idea behind how we were able to expand the operating system beyond 64 without impacting compatibility, without changing some of the basic assumptions that we make in the kernel. This is just another look at how this would relate to a 128 processor system. In this case, you'd have two groups. Within a group, you might have multiple NUMA nodes. And that's important because a NUMA node cannot span groups. Then inside a NUMA node, you have a socket, a core, or multiple cores, and then you're likely today to see hardware threading. So you might have two or more logical processors. So this is the big announcement. And we announced this morning. We're supporting up to 256 logical processors in Windows Server 2008 R2. Why that number? That's the biggest box we can get our hands on right now. We got one of these helping heat Building 26. We'll take a look at what it is later. Again, we're targeting these single line of business applications. For us, the game is Windows Server and SQL Server, but we're looking at SAP and other applications as well. In a moment, I'll look at this, but one of our biggest challenges was refactoring some of the hot locks. We also had to affinitize or make aware our storage and network stacks. And what's really important about this work is we were doing this a year and a half ago. A year ago, we had systems running 128 processors on Win 7 builds in Building 26 at Microsoft, and we were starting to do performance benchmarking. So this was very foundational work done very early. Again, not a minor release at all for those of us in the kernel team. So this is where we were a year ago. We had scaling numbers where if you go from 64 logical processors to 128 logical processors, doubling everything, doubling the amount of memory, number of I/O, storage, etc., we were running into Amdahl's law, which is basically that the lowest common denominator is going to slow you down quite a bit. In our case, it was the dispatcher lock. It's a big, clunky lock that we've used in NT. It simplifies a lot of the work in the kernel, and we haven't had to touch it until now because it simply wasn't getting in the way. Started to at 32 and 64. We did a number of a conservative number on scaling, and we go to David Cutler, who is a Microsoft fellow. He's the chief architect of Azure, and he's the father of NT. And Arun Kishan, one of our young principal architects or developers on the kernel team, wanted to go after this really badly. It's one of those stars you can put on your collar. And Dave said simply, "There's no more fat. You either really have to stretch, put the platform at risk maybe, or you accept this and maybe think more about scale out." Working nights and weekends back in the spring, and under cover of darkness because we weren't using any of our internal tools to track this work. We actually did all the documentation for this after the fact. Arun was able to jump performance numbers on the same system up to 1.7x scaling. This is about where we stand now. We're still working on some further optimizations. I'd love it. But this is pretty good scaling, going from 64 to 1. Now that we have all the documentation in and it's an actual feature, it was in early, and this has really been talked about within Microsoft with execs such as John Devon, Sinofsky, and Bob Muglia on the server team. So this was part of that great amount of effort that went on the kernel team as we prepared for this release. This is a quick look at the hardware evolution. Today, systems look pretty simple. We're starting to see these NUMA servers, and that is where, as you start to spread out, things become near and far. And the operating system and drivers and firmware have to start becoming aware of where these different NUMA nodes are in the system. Legacy devices, and you see device A and a normal application below, operating system will pretty much take care of you as long as you only need to operate within one NUMA node. We'll also round robin, and we'll talk more about that later, but we're pretty smart about spreading a number of applications and processes across the system. It's these scenarios where you have a product such as SQL Server, where that team has been doing tremendous efforts to scale also up with us. And these benchmarks we were looking at were SQL Server benchmarks. And we're scaling, we're now looking at NIC and storage devices also that need to be aware of more than 64 processors. And this is just kind of a foundational slide. We'll go into more of these concepts later. Hand in hand, and part of this, it's not really a minor server release for us theme, is other work we've been doing. And the first one is critically important because these large systems are some of the stickiest decisions in IT. They run your business. They're incredible investments, not just in the hardware and the software, but in support and in all the other applications throughout your system. People don't look necessarily at price first or even performance first. They look at reliability. And these commodity systems are going to be predominantly x64. And one of the big goals we have in Windows Server 2008 R2 is to bring x64 reliability up closer to parity with IA64. And we're using Windows hardware error architecture to identify errors. It works in conjunction with features such as dynamic partitioning, so that if you get a certain number of errors, we hit a threshold, you can replace that unit before it fails. And we're also working on having the ability to correct ECC memory errors, or MCA memory errors on the fly. So there's a lot of work that's being done in regards to reliability. The next big topic, and this could be a talk in itself and will be at WinHack, is server power management. Data centers today are 2% of the US electricity budget and growing fast. That's why we build them right next to big power sources. This relates to the whole server ecosystem, especially things like Azure and big data centers. But it goes hand in hand with scale up as well. And some of that are the opportunities around having lots of cores and being able to power down cores when you're not using them. And so just briefly, I'm showcasing core parking here as a way of making servers more power efficient. If you're not using a core, the OS and software can park it, put it in a maybe just for milliseconds in an unused state. The underlying hardware then will put it in its lowest possible P state, processor state. That saves power on the system. Today's servers, even at idle, usually are at about 70% power consumption. And we're working very hard, not just ourselves, but with our hardware partners to bring that way down. And these are big pushes for Microsoft. It goes way beyond just the scope of this discussion today. Virtualization. Virtualization also relates to power management. You're able to instead of having servers that on average are running at 70 or 80% of their power consumption, but only at 20% of their capacity, with virtualization you can start moving those workloads around. So it's also critically important. And these are other areas that you see very big leaps in Microsoft this year. So this is the guts of what we did to support more than 64 logical processors. Instead of going with like a linear design where we simply say, okay, we're going to have processor number 65, 66, 67, that was an option. But then we're breaking a lot of underlying assumptions, breaking a lot of apps and drivers that work today, and would have taken pretty significant changes to the operating system. Instead, we came up with this idea of groups, and you can see we're all within a single group 0 here, and then down below you can see group 1, group 2, etc. And what this does is allows us to always have a legacy environment. So if you're an application that today is affinitized to 64 processors, you're still always going to see 64 processors. As long as you're not doing something that's a corner case, like making an assumption about processor number, because now you can have the same processor number in 2 groups, we expect to have a very high rate, extremely high rate of compatibility with existing systems. We started early on this project, and we also started early with engagements in this project. And the big focus, and actually I'll start back a little bit, even before these engagements. We started down this path partly because the server org came to us and said, we have these customers that are asking about greater than 64p support in Windows. And we said, well, are they really planning to do that? And they said, no, but they might in 5 years. And they're making big, long-term decisions. They want to know, are we going that way? That really got us thinking, and that's what really got us moving early on this. The next thing that came up is we started talking, started looking more closely at some of the Intel and other roadmaps we were getting. And we're starting to see some of these, and Lena will go into this in more detail, we're starting to see some really amazing stuff where you have, for example, a single node commodity server that's going to be at 64p next year. And that really started getting us going. And we got the work done early, and we've been engaging closely with Intel, AMD. We've got HP and Unisys systems in our labs, as well as an IBM Athena system. Most of the hardware we have now is Big Iron, but it's what we need for development. And you see we've been working with some others here as well. SQL Server and us, we meet once a week. We have been for 18 months. So that's a very close collaboration. We're reaching out to SAP and some others. And I'll probably repeat this a few times, but if anybody in this room is writing an application that scales beyond 64p, we'd love to talk to you. That goes, you can leave right now because we're going to want to talk to you a lot. And you'll hear all this again. So just let me know. Beyond this, we're also working with teams like the Concert team, the concurrency runtime team at Microsoft, and they have all these crazy ideas about clients with hundreds of cores, and we'll see, but we're certainly keeping that in mind as we move forward too. So we're thinking about client as well as server in our engagements. This is the system that's currently heating Building 26 at Microsoft. It's a HP Superdome. This is an IA64 example, and I'll do the math for you. You've got the Montvale 9100. It's a Intel scowling at me because it's a little bit older processor right now, but it's a 64 dual-core hyper-threaded. So 64 times 2 dual cores times 2 because it's hyper-threaded. That's how we get to 256 logical processors. Terabyte of memory. This has been a great machine for us. We're working right now. We just got this in this 256p configuration. We're working right now on getting benchmark numbers on this guy. The benchmark numbers you've seen so far are up to 128p. Here's another example, and Unisys is taking a little different stab at the market. They're focused more on the Xeon side, which we find interesting, and we think there'll be more of this moving forward. In this case, you've got 32 dual-core hyper-threaded. So again, 32 times 2 times 2 for 128p. Only 256 gigabytes of memory only. And this is a system that I'll show you in a moment. We did a lot of our scaling work on. And again, that's the Tulsa Xeon processor. That's no longer on Intel's current roadmap because it's just passed by. I think this is current more like a year ago. So this is a performance benchmark we're running on that Xeon system. And this is Task Manager looking at, and I'm sorry I couldn't bring the system here today, which would have made me really disappointed when only 10 people showed up. But we have, you have 16 rows across, 8 rows down. The great thing about this is a real benchmark running SQL. The great thing about this benchmark is, for the most part, you'll see that we're at pretty consistent CPU usage across the system. We have a little bit of some spiking there on 3 processors in the upper left corner. I'm not sure what that is, but that's the type of analysis our perf team's been doing. Occasionally, we'll find reasons to tune things based in either the SQL team or our performance team. We'll be looking at this to make sure we're getting full utilization out of CPUs. And we're at about 70% utilization in this sample. We had a lot of discussions with the task manager guys about how to show this. It was the UI discussions have been interesting. Kind of not something I'm used to working on, but it will be important in the future as people start to run on these large systems and they need to do diagnosis and understand what's going on. A big scare is application compatibility. And I think I already talked about how you should have a single group view. So unless your application needs to view 128 processors or it needs to scale up to 128 or 256 processors, in which case you should come talk to me right away, there's not a lot to worry about here. There is zero app-compat impact on existing systems. This feature does not, on systems with less than 64 processors. This feature does not affect application compatibility on 99.9% of the systems out there, with no possibility. On the 1% that are huge scale-up systems, there's still a very minimal chance of impacting your application. We've got some new structures, and this is just a sample look at the new structures we have for processor and group. So now you always, instead of just having a processor number you're indexed, you've got processor 8 on group 0, or processor 56 on group 1. And that's kind of the future construct. I'll go through this pretty quickly. They said they said we weren't supposed to do a lot of in-detailed APIs after 5 o'clock. We'd lose people. Thread and process affinity. And this is just to kind of show how we're handling by default apps. By default, we round robin across groups. So if you have a multi-group system today, you don't have to worry about all your applications just running on group 0, and then you're not using CPUs 65 through 128. We're gonna do the logical thing, spread things around. Applications, there are lots of sexy APIs for overriding this stuff. And we'll see this in the next slide too. It's kind of the same thing at the application level. There are a lot of APIs where now you can make your own decisions, you can override this stuff, but be careful if you're not paying a lot of attention to NUMA and topology, you can actually easily make things worse. So there is a big evolution for people writing apps on these big scale-up systems moving forward to really start being NUMA aware. And we're going to look at some more examples of that here soon. Here are some new functions, and some of these are extensions of previous APIs, and some of these are new APIs. The first couple here are group-related. And then we see some that are processor count and group affinity related. And the processor count ones are now interesting in that depending on what argument you give it, you either get the number for total number of processors on the system or for processors within a group. So we're giving folks a lot of flexibility moving forward. Something we aren't going through here in detail, but will be in a white paper. And we have a white paper with all this information that's coming out next week with WinHEC that's referenced in the back of this slide. So it's not a dead link, but it's a coming soon link right now. But we'll have detailed information. But again, if you're writing some of these applications, come talk to us. We'd love to talk to you. NUMA nodes, let's go into a little bit more detail around non-uniform memory architecture. The first thing to say is it's coming on servers, and we expect it to be ubiquitous in the future. So if you have apps that have to scale, certainly if they scale beyond 64 processors, but if you have apps that have to scale even to 264 or 232, this is something where you want to start becoming more aware as we move forward. Processes and threads can set a preferred NUMA node, and that means the operating system will do everything we can to keep operations within that NUMA node. Should help performance in most cases. And also the whole architecture behind the group idea helps performance, because if you're running a legacy application, it's always going to say in a group, and a group contains NUMA nodes that are in logical proximity to each other. So you're actually more performant because you're within one group than you would be if you were spanning groups. So this is a picture that always confuses me, but this is a really bad case. You have a system here with two NUMA nodes, one on the right, one on the left. You've got a node interconnect in between. And the whole idea is to keep I/O processing on one side, not to do this crossing back and forth. In this case, you've got P3 that does a disk write across the interconnect. He stalls P2, validates some memory, grabs some data, and this starts to get ugly really fast because we have a lot of housekeeping, we have a lot of cache coherency we have to clean up, and we just have delays as you cross the interconnect. This is a two-node system. Imagine this on a system with 16 NUMA nodes, and the complexity really can dramatically affect performance. So we expect some big scale-up applications and even some medium scale-up applications to start to run into this with new hardware architectures. This next slide is ideally how things should work. And we have some new NUMA APIs that will also be part of that white paper coming out. And here you can see the same type of interaction. And we're keeping completely on the right-hand side here without having to impact processor 2 or processor 1 on the other side. And this is just an ideal situation. So the system topology APIs give you the view of everything you just saw. They can tell you what they'll return what the firmware has to know, and this again you need to have really good coordination with well-built OEM systems with the proper firmware to really give you the right information as to what I/O and memory and processors are in proximity to each other. If the firmware lies to you, then you're out of luck. But all the OEMs we work with do an excellent job with this. Memory topology is exposed as well as even cache levels. And we're seeing more and more that I/O is becoming part of NUMA. For system tools, we have perfmon, task manager, which you saw, and resource monitor. Unfortunately, most of you don't have a 128p system to play around with, and we weren't able to bring one today. But these are some tools that in the future developers will be able to look at and not only just see where every processor is, but see what node it's a part of, what NUMA node it's a part of. And the types of problems you saw in that demonstration before with the animation is what you'll be able to understand through the UI and tools available with the system. We also expect there to be, hopefully, to be some down the road, some third-party tools as well built on top of this. With that, the importance of what we're doing goes hand in hand with what Intel's doing, especially around Xeon. And I'll introduce Lena to go ahead and give us a talk on some of the Intel roadmap features. Leah?
Thank you, Ari. Hello. I'm Lena Pudiedat, a senior architect at Intel. And as Ari went through, for the greater than 64-piece support in the operating system, the hardware is right there, or before it. So the evolution of Intel's multi-core, multi-thread has made it happen that the demonstrations on the Itanium and the Tulsa platform that Ari just displayed continues in our future roadmap.
That's actually my cell phone.
Oh, sorry.
Sorry, I didn't hand this off correctly.
Okay, so that's Intel's enterprise roadmap. And as you can see, we have top to bottom leadership products with our quad-core 45-nanometer technology. It's available today in 2008. And we are very excited to continue that leadership in our future roadmap with the Nehalem architecture-based products coming soon. So this is an example. This is an overview of what is the Nehalem architecture. And this gives you a visualization of the multi-socket, multi-core, and NUMA impact that Ari has already mentioned. So, the first picture shows two physical CPUs, and the memory and I/O have point-to-point interconnect with the CPU. So all of the CPUs, the memory, the I/O are all connected point-to-point with a fast interconnect, and we call it the Intel Quick Path Interconnect. And so the memory that is local to a CPU is the near memory, and the memory that's local to another CPU will be far from the other CPU. So this is what is the non-uniform memory access that Windows Server 2008 R2 is optimizing for. And each of these physical CPUs can be 2-core, 4-core, 6-core, and with hyper-threading, that's twice that. So as many logical processes. So you can have 16 logical processes in a single physical CPU. And when you go to a 4 CPU configuration in the right-hand picture, so there you immediately have 64 CPUs in a single node controller platform. And so this is right here. This is the kind of platforms that Windows Server 2008 is targeting and optimizing for. Sorry. So this is a big picture of, there's both in the server workstation segment and in the client segment, we have increasing number of logical processes, but it's a server segment that will have the majority, the greater than 64 logical process that we are currently targeting. So basically, what does, as the number of logical processes increase in the platform, what else should change to address that? So basically, as each CPU, each logical processor has to be addressed to have something run on it. And with the current architecture, that addressability is getting strained with the increasing logical processor count. And so I'll give you a brief overview of what is interrupt addressing. So each logical processor has an address, and that we call an APIC ID. So this ID is not just an just a sequential number. It actually it encapsulates the topology of that CPU. So as Ari mentioned, so which socket, which core, which hyperthread. So all of that information is embedded in that ID. And since P4, we've had an interrupt architecture called XAPIC, which uses an 8-bit value for this APIC ID. And with 8 bits, you get values up to 256. And so the physical, there are different ways to address a CPU. And the physical address is the actual, the ID, addressed by its ID. It's limited to just 254 because 255 is a broadcast. And another mode of addressing where you can address multiple logical process in a single message is called logical mode addressing. And in a logical mode address, we can only address up to 60 logical process. So this is the kind of addressing that the today's OSs use. Windows Server 2008 uses XAPIC addresses and logical and flat addresses. So with moving forward, I mean, this has satisfied the requirements of the older process. But moving forward with Nehalem processors, we need larger addresses. We have a single a single socket will have 16 logical processes, and so the current XAPIC architecture already has hit the limits of addressability limits for Nehalem platforms, and with the current architecture, it can only address up to 128 logical processes on a Nehalem platform. So what we need is the next generation interrupt architecture to address the larger number of logical processor counts. And that's Intel's X2APIC, the next generation interrupt architecture designed to meet the address scalability requirements far out into the future. So we meet that with a 32-bit APIC ID. So with 32 bits, you can go up to 4 gigabytes of addressability, 4 gig addressability. And changing the interrupt architecture is something fundamental in the platform. It's not something that you can overhaul without a substantial effect to the rest of the platform. And in order to maintain compatibility with the current devices and specifications, so PCIe, PCI, IOXAPIC, we decided, I mean, compatibility is the bread and butter for both hardware and software. We don't want to completely overhaul the entire ecosystem with new devices, new drivers. So we maintained absolute compatibility with today's devices and protocols with the X2APIC. And how did we achieve it? So if you're a device, how do you address these larger processors. I mean, today's devices, they just use an 8-bit APIC ID. So how do they address the 32-bit APIC ID processors? And here we leveraged a feature that was initially intended for device virtualization. So Intel's virtualization technology for direct I/O, it was initially designed as a virtualization feature, but we enhanced it to support the extended addressability in the device path. And what this really means is that while the devices don't have to change, the platform needs to support we call it VTD2, the Intel Virtualization Technology for Directed I/O, and it's a platform level and BIOS level support. And correspondingly, the ACPI 4.0 specification that's in the works is augmented to enumerate the 32-bit APIC IDs. So all of that impact is really contained in the operating system and VMM support for these additional technologies, for the X2 APIC, for the Intel Virtualization Technology for Directed I/O, for the ACPI 4.0 extensions. All of these changes are contained in the operating system and VMM and the BIOS. And if you are a device driver writer, you are not impacted. If you are an application writer, you are not impacted. So a whole substantial amount of changes happening underneath you to hide the effects of it from the applications and drivers while providing the scalability. So that was an intentional design, and that's what we have achieved. So I'll hand it back to Ari.
Again, I need my mic on. I could just start shouting louder. So again, okay. I should be good. Here we go. Again, this isn't really a minor OS release for us. You know, we're working closely with Intel now, and as long as the timing is right, we've already done the feature work to support X2 APIC. If we get the Nehalem systems we need in time to validate this, this will be part of our initial release of Windows Server 2008 R2, which I expect it will be. If not, it will be in the next chance after that. But it's, again, an example of the foundational work. I'm just going to go back a couple of slides here, because the real wow for me is this Nehalem system on the right, the EX system. That's a commodity system with commodity Xeon-based x64-based system with 64 processors. OEMs are going to have a heyday with this. I mean, folks like Unisys and HP, they'll be throwing together maybe certainly 2-node systems and 4-node systems, and they're going to be up there competing with Big Iron. This is a really fundamental change for us. Something else that I should mention, not just because my management asked me to, but because it's also the way we're working, the mentality we have on the kernel team, is that with all these features you're seeing, with the scale up and the new topologies and NUMA and server power management and Windows hardware error architecture, these are all areas for differentiation for the OEMs. So we're in a tough climate where, in a lot of areas, folks have been driven towards commoditization, and these new a lot of this new work that's coming forward, and even though you see Microsoft and Intel at the forefront of that, there's a lot of opportunities out here for hardware makers, for software as well, and that's what's really fun and exciting about this. One aspect of it. It's not just the evil laugh thing where we talk about taking over the Big Iron server market, which we'd love to do. Now we'd like to look forward at scale-up futures, and we start thinking about both server and client. We certainly know that virtualization and hypervisor will continue to scale in lockstep, but a bit behind where we're able to scale with the operating system. Power management moving forward continues to be more and more critical. You may even see in the future, theoretically, processors that become less powerful, and we're seeing some of this already, but there are more of them spread across the system such that we actually reduce power consumption as we increase processing power. WIA for client. You know, if you start to see client systems with hundreds of processors someday, you may need to have some spare cores on hand or some spare processors to make sure that your system has a high level of reliability. That's something we're not sure if it will happen or not. You know, you kind of have these two visions. You have Azure and computing in the cloud, but it doesn't mean that we also don't. And in that case, you're dealing with thinner and thinner clients. On the other side, you've got amazing potential for some really big client hardware. We've been working with the Visual Studio team, and they're releasing Visual Studio in 2010, in which case that in the kernel and in our threading mechanisms, and we'll show you a bit more, we're providing them the resource management and scheduling they need for concurrency workloads. And what that means is after 2010, using their concurrency runtime, you'll be able to build applications that don't require knowledge of how to handle parallel processing or concurrent processing on top of their runtime, and you'll start to gain the benefits from these larger and larger systems. This Visual Studio 2010 release will include programming models, tools, the runtime, and rather than try and talk to their information here, I really encourage you, if you're interested, to go out to MSDN and look up the concurrency link. So this is something that we came up with initially. Honestly, initially we were thinking about this for SQL, and it's called user mode scheduling. It's not really, there'll be some public APIs, but it's not something we really see third-party applications using today. But it is something that we'll see the concurrency runtime leveraging, and you'll get the benefits inside of Visual Studio 2010. And essentially what we're trying to do is solve the problem of thread switching, where you have lots of kernel incursions every time you switch out a thread from a running thread to a non-running thread. Today, this is pretty high cost when you get to these systems with hundreds of cores or hundreds of logical processors. So in the future, we're giving applications and runtimes the ability in user mode to switch out user mode threads without kernel incursions. This is much less impactful. We are seeing some benefits of this with SQL, but after that Hail Mary pass we made with the dispatcher lock, we actually were able to come to a situation where, in that case, there is some performance benefit, but it is not as dramatic as we'd originally hoped. But the parallel computing program team started using this, and they're now working with our builds and incorporating this into their models. So this is some really exciting work. It's very incubatory. You know, this is work where we're thinking many years ahead. You know, there are some other concepts that we're building on here. One is if you can start to do things, and this is thinking way into the future, but if you can start to do things up in the user mode without incursions into kernel, perhaps there are models we can use there to abstract, say, a core that doesn't have the same ISA as another core. So we'll skip on to the call to action today, and I'll bet that there are very few people here who actually are needing to leverage the topology APIs. but this is certainly something to think about as your business moves forward, as you start thinking years ahead. This will become more and more important, and we'll be coming back both at PDC and WinHack with more and more detailed information, especially as the market and the products come to fruition. If you do have tools or applications that need to be enlightened, please do so. Check the white paper and talk to us. You'll get a lot of attention. Certainly implement support for X2 APIC. That's more for the hardware vendor side. If you represent a company that's invested in big iron, you're running SQL or another large database application, and you're thinking years ahead, we really want you to, we know those are sticky decisions. We know you have a lot invested. But that's an area where you really want to be looking at what we have to offer on these, for example, the Nehalem type platforms, running Windows Server, running SQL, the cost savings and the competitive push that we're putting into this we really expect it to change some decisions out in the marketplace. Here's some resources. That first link is coming soon and should be live next week when WinHack kicks off, also here in LA. The Windows Server Performance Team blog, a lot of these slides, such as the NUMA slides, came from Windows Server Performance Team, and these guys have a great blog out there. So if you have questions based on performance, that's a great place to go. Again, MSDN for concurrency runtime, and we have links here for Intel's architectural specifications. Again, please fill out your evaluations, and we have recordings of this at microsoftpdc.com. So hopefully we have a lot of folks who weren't able to make it today because this was a double secret session, and they'll be able to view this later. So any questions? Feel free either to do a formal Q&A or just to come up. Lena and I are available.
So I actually have 3 questions, primarily around the NUMA stuff, and that one diagram with the 4-node Nehalem architecture. Do you guys have an estimate on if you have to go cross-node for memory access, like how many times more expensive that is than staying within your own node?
It's going to be costly. So the operating system has to be fairly aware to try to keep the application accesses as local as possible, because it'll impact the visible performance of the application.
Okay.
I can get you a more, if you want to send email to that alias, our performance guys will give you an answer, and it will be one of those really detailed answers where it's based on what architecture you're talking about.
Yeah.
Okay.
Usually it's, depending on the case, it's often 1 point something or more, but that's a really, really general answer.
Okay.
Yeah, it can be 1.2, 1.4.
Okay. A follow-up question to that was, if, say, there's the 3 other nodes are all trying to access memory on your node, then even though you're not doing anything wrong, you might actually be impacted by other people's poorly written applications, right? Because your memory controller won't be able to keep up? Okay.
Yeah.
And then my third and final question is, you kind of have interlinks between all the different nodes in that diagram.
Yes.
And that to me seems like it wouldn't scale when you had lots and lots of nodes. Are
So
you guys thinking of like hierarchical nodes?
So it is a point-to-point interconnect to try to keep the latency as small as possible. And so the Intel QuickPath architecture is optimized for that point-to-point connectivity.
Okay, but there's no thought at this point of like nodes of nodes and kind of groupings of nodes or anything like that?
OEMs do build larger systems. So the picture I showed you of the 4 sockets, OEMs could build multiple of those with interconnecting node controllers.
This kind of comes back to that the opportunities for OEM differentiation are high here.
Yeah.
And they could end up doing something unique. Right now, I don't expect to see more than maybe 2 or 4 node systems, but how those 4 node systems are and how they connect, that could be very interesting.
Okay, cool, thank you.
So the question is, we could have a single socket that has more than 64 processors. That's really far out. And the question then is, could you potentially have more than one NUMA node? And I would have to check my ACPI specification, but my guess is no, the way things are currently specified. But with those types of evolutionary hardware changes over time, if there's a need for it, then we go to the standards groups and we work with the industry and we come to a solution.
Actually, I do.
Or maybe she knows more than I do.
So the ACPI specification has what is called an SRAT table, a system resource affinity table that enumerates the proximity domains of the processors and the memory, and doesn't so it is only listing these APIC IDs are near to this memory, and it doesn't necessarily have any association with the actual topology. It doesn't limit, meaning it doesn't it doesn't limit multiple sockets being part of the same NUMA node or multiple NUMA nodes being within the socket. So that's the specification does have the flexibility.
Yeah, and I think we also have flexibility within the software. All right, any other questions?